Swayam Prabha. Digital India. Educated India.
Good morning, students. In the chapter on the kinematics, the two-dimensional motion is planar kinematics of bodies. We have done some examples on the rod sliding on the horizontal ground and so on. So there is another very interesting example is this, a disc rolling on the ground. You can consider it to be a disc, or you can even consider it to be a cylinder, just like they put the cables and then pull the cable out and so on. So there are three interesting cases, sometimes thought-provoking, sometimes intriguing and so on. So that is, this is a cylinder in which you tie a rope here and then pull with some force F, and so obviously you can see that it rolls and moves to the right. So similarly, there is this is just without any rope. So there sometimes the cable is wound around a smaller diameter. Maybe you can say that this is R1 and this is R2. R2. So that means that on a smaller drum here, R2, which is the integral part of the main cylinder, there is a wire or a rope wound around, and then you start pulling it from the top. A similar one here, exactly. Only thing is that the rope or the wire which is wound around, so you try to pull from the bottom. So both are possible. So each is an independent analysis. I mean, the results are quite different from each other. So let's assume something, that there is a friction, and of course the mass is, and then the radius, outer radius is R1, and then a smaller drum here, drum radius R2, and then there is a force F applied. There is also a friction, coefficient mu. There are two types of frictions, of course, the static friction and kinematic friction. So as long as there is no relative motion at the point of contact, then we put the static friction. But the moment there is a relative motion takes place, that means that the sliding is taking place. So you have to apply kinematic friction. So the kinematic frictions are slightly smaller, but anyway, for this sake, so let's not really differentiate. Our emphasis is something different. So let's not put mu s and mu k, both are same. We'll take it mu s and mu k. Let's just keep it as mu only. Okay. And then there is also another important one, the radius of gyration is k for the cylinder together with the drum and everything put together, maybe including the wires as well. So that is radius of gyration is k. Okay, so which essentially means that the I here, mu k square, okay, mk square. Okay, so I hope you have understood the problem here. So there are three different cases of a cylinder rolling on the ground, and we would like to analyze it. What will happen when f is small or when f is large? That's the main classification. That's first classification, and then there are a few other, definitely other salient points. So the question now is that let us just do the first case. In which we have a force being applied at the center, G, and then if you draw the free body diagram, that's what we are doing, FPD. So there is a normal reaction here, and there is of course a weight, and then there is a friction also acts here. The friction F acts like this. Is the friction going to act like this or the other way? Okay, actually the friction opposes the main applied one, main force which is being applied here to drag, and so together they will create a couple. So this is equivalent to a mass times acceleration. So that's here. Okay. And then we also have I alpha. So this is, we put with it results in linear acceleration of g and an angular acceleration, and this together with m will become the force, and this multiplied with I will become the couple of the moment. And so these two are equivalent. These two systems are equivalent for all our engineering mechanics considerations. So not for consideration of internal forces or stresses, not for that consideration, but for the analysis of our mechanics. So this is what is equivalent. Okay, so this is the free body diagram. So in the free body diagram compared to the statics, so we show the actual forces, and this is the effect of the forces. So that is our, so anything, whatever you do on the left side, you can do on the right side and equivalent. So now the question is that the force is small and F is small, and so that there is no slip here. Okay, so case 1 is F is small, so there is no slip at the ground, at the contact point, at the ground. And also, so that means that this ground point, so which essentially means that the force F here, and N is equal to W, that's very trivial, and F here is definitely less than mu N or mu mg, right? So that's what we assume when the F is very small. So this is the case. Usually what we have to do is that we assume something. So what is the assumption? That there is no slip here. And then finally, when we evaluate all the parameters, we should make sure that this condition does indeed satisfy. Okay, so then what are the other equations? So the other equations are in the horizontal direction. So it is F minus F is MAG. And what else? So we have to take the moment equation also. So this is the horizontal equation, this is the vertical equation, the moment equation about some point here, and that point you can call it as C. So moment about C is that F into R1, so this is the radius R1, and F times R1 about all of this 0 here, and so that is equal to Ig times alpha plus M Ag times R1. So to solve these equations, so one simple thing is that we will substitute this one as mk square, and another very important fact here that there is no slip here makes us use, so no slip means, so it's a pure rolling. So which means that the velocity of the center point is omega times r1, and similarly the acceleration of g is r1 times alpha. So this is the, so these two things, no slip and then that's called pure rolling. So this is, they go together. So this is what we are assuming. Okay. And so using this, so what we have here is that substituting in this third equation, so it is FR1 mk square alpha and MAG R1. So all right, so using alpha is as Ag over R1 plus MAG times R1. So this is a very simple manipulation. So we have, so M, so what we have here is that R1 is square plus R1 square, okay, times so which gives us the acceleration here, FR1 square okay. So this is what is the angular, linear acceleration. So you can also find out the angular acceleration here. So when we said that f is small, so the question is that how small is this f? So this is small as long as there is no slip. So as long as this is satisfied. So it is possible that the friction that is necessary here, okay, in fact we can even calculate f here. So what is that f? So f is, we can also calculate f here, f minus mag, so which is nothing but m times ag you can cancel, and k square plus r square, so it is nothing but k square plus so the F, that's the friction force here, is a fraction of f given by k squared plus k squared plus 1 squared. So the obviously as f increases, so the acceleration increases, angular acceleration increases, and the f here, this friction force also increases. So this friction force can increase up to a point given by this one, given by this limit. So the maximum f you can apply maximum f that can be applied till f is equal to mu times n or mu times w. So if you can call that as a critical value, you can do that. And so that means that you have mu times w is equal to f or this is, if you call this as f critical, so it is mu times mg okay. So this is the critical value. So this is the maximum f which you can apply is this one for this condition to satisfy, that's pure rolling. Okay. So once you go beyond this, so the case 2 is that once f increases more than f critical, then what happens? Then f can no longer sustain this maximum force, and it is limited to, f will be limited to mu times w only. Okay. So you cannot go beyond this value, and f will be limited to mu w. So that means that now if you draw the free body diagram, again modified again, so this is a modified diagram, and so what we have here is this. Okay, and this is n, which is equal to mg, and this is f mu mg. This is the maximum value. Okay, and so it is no more related by other means. Okay, so this is again, the right side will remain same. So this is much easy to calculate. So n is mg, n is equal to w, so which we have already put it. And so again, we can put the horizontal equation. So it is f minus mu mg is equal to mag. So which gives you acceleration of this one is nothing but f by m mu g. Okay. On the other hand, you can also take the moments of these forces about the bottom point C here. So the other thing is that F into R1 here, okay, will be equal to I alpha here. So which means that it is F by alpha is equal to FR1 divided by I, right? And this is nothing but okay. So this is interesting case, okay. And so there are two cases. So that means that in the case 1, so in the case 1, we are assuming that there is no slip, the applied force F is a little small. That's the assumption. And how small is that? That's what we evaluated later. So then we assume that F is a small value, variable value, depending upon what big F you apply. And then we applied the equilibrium equations in the horizontal direction and of course in the vertical direction, and then the moment equation. From that we found out the AG and also alpha, right? AG and alpha we found out, and then in that process we found out the friction force F needed, and so this is what we got. Okay, so this friction force, we know that the maximum value this can attain is given by mu W, and adding that here, so we can find out what is the maximum F or F critical you can apply. So that's what we say. So once you go beyond this one, so F cannot increase more than mu W, and then it is limited to mu mg. And then we recalculate the whole thing, and this is how. Okay, so this is the interesting part, and this is whenever you have these kind of problems, whenever you have problems involving friction, we always follow this procedure, in the sense that we assume that there is no slip, and then we calculate everything, and then at the end of it we have to make sure that the friction force is less than the maximum allowable value, that's mu mg. So you have to show that. But on the other hand, if it violates, then you have to recalculate everything by putting the friction force equal to its maximum possible value, which is mu times the normal reaction. Okay, so this is how we do these problems. So let's say there are other interesting cases here. This one, I'll leave the other case to you as a homework. So here we have a drum on which we wound a rope or a cable, and then we are pulling out the cable from the bottom. Okay, so again here, obviously it starts rolling on to the right side. Okay, so with some linear acceleration for the point G and angular acceleration alpha for the whole thing. So let us draw the free body diagram. So when you draw the free body diagram, so these are the forces. This is R1. This is R2. Okay. So these two are seems to be pretty similar, but the analysis shows that the results can be altogether different. So there is a W there, and there is a normal reaction. Okay, so there's a friction force F here, and this is equivalent to or equivalent Okay, so the free body diagram looks almost same, except that this horizontal pulling force on the rope is shifted by a distance of R2. Okay, so we can go through the same procedure. So again, we can put down, so when assume that F is small, just like in earlier case, and in which case there is no slip at the contact point. Okay, and then F is less than mu n. So this is need to be verified or put a condition on what this means. Okay, so these two are associated. Okay, so now the thing is that we go through the same equations. So the vertical equation is, of course, n is equal to W, and then we have, again, we'll use the horizontal equation. So it is F minus F is exactly the same thing, and F times, now it is R1 minus R2, take the moment about 3 here, okay, is equal to I times alpha plus MAG times R1. And of course, when there is no slip here, so we can convert AG into alpha. So no slip. So the kinematic constraint is that AG is equal to R1 alpha. Okay. So this is the various conditions here. Just like we have done earlier, we can do the same thing here. So we will evaluate AG and alpha. So I'll just quickly go through it without really. So solving those equations. So we get AG okay, and alpha is, of course, AG by R1, and using these equations we can calculate F. So that is R1 R2 okay. So solve it, this is what you get, just like we have done earlier. So and then simplified, this is what you get here. Okay, so while there is no slip, for no slip, F can become maximum of mu times W or mu mg. So using that, we can calculate so therefore F or F critical obviously will be mu times mg So these equations seem to be quite similar, but again now we are getting R1 and R2. Okay, so this is what the maximum F you can apply so that there is no slip, and beyond that obviously there will be a slip. Okay, that after this, when so the case 2, when applied force is greater than this value critical, then we have to modify the free body diagram. Just like last time we did. So F is equal to mu mg and okay, so by going through these equations, so apply those three equations. One is W is equal to N in the vertical direction, and in the horizontal direction F minus mu mg, now it's not F, is equal to mag, and then you have to take the moments about this point. So F into R1 minus R2 is equal to I alpha and times mag times R1. Okay, so from this, so we will calculate Ag will be minus F into R2 mk square Okay, so that's what we get for these things. So the interesting part here is that the end results are completely different. So what we would like to see here is that when F is small or when F is more than F critical, so what will happen to this rope here? So some guy here is pulling this rope with a certain force, right? And what will happen to this rope? Is he going to pull the rope out, in the sense that can he say if there is some 10 meters of rope, can he pull it out and that complete 10-meter rope, or what will happen? So interesting things will happen here is that to calculate that one, so what you need to do is that so let's look at So there are important points here. So here we would like to look at the velocity of A and velocity of B. So velocity of A is the one where how the disk is moving, and velocity of B is attached to the rope here, how the rope is coming out relative to the disk. So what does that mean? So if you calculate here, so actually it's like this. So once you know the velocity of A, or velocity of A and velocity of G is nothing but, what is that? It's nothing but acceleration of G times E, right? So acceleration of G is, say, constant, and then you multiply with so this is a uniform acceleration. So you in the initial interval, and then later on it will become again constant, so with some other value. So similarly here, so if you want to get velocity of B, so what is that which we have to get? So velocity of A plus B with A. So velocity of A is nothing but your velocity of, G, velocity of C, and then so the velocity of A is like this, and velocity of B is velocity of B with respect to A. So the angular velocity is like this one. So it is minus omega R1 minus R2. So this is the magnitude, right? Everything is horizontal, and then you can even write VA. Okay, so that means that the velocity of B here is less than that of velocity of A by so much of angular velocity here. Okay, so initially if you look at the graph, for example, if you look at the graph here, if you look at the graph, so the acceleration of G is increasing like this, and then just we'll also show alpha here, same graph, and then this is with F. So in the during the first phase, so this is how it is going to take place. So you can also draw the velocity here, and then what happens later? So this is the F critical. After that, what happens? So if you look at these values, and then if you look at dropping this, if you look at this one, so then this starts decreasing and this starts increasing. Okay, so after this first phase, so both will be moving. So this is moving forward, and then this is also continue to be clockwise. But after some time, what happens is that this starts decreasing. At some point, this is becoming 0. So, and then it becomes negative here. So what does that mean? This point, when F is this value here, this is the first, and then this is the second critical value. So when at this second critical value of F, the alpha is 0. So what does that mean? If alpha is 0 here, so we have seen here, if alpha is 0, so omega is equal to alpha times t for uniform acceleration. So when alpha is 0, so that means that the angular velocity of the disk is 0. So what does that mean? So that means that it's not rotating, but A is moving in this direction. A is moving, but it's not rotating, which means that B is also having the same velocity. Okay, so at that point, the rope is velocity of A and velocity of B are same. What does that mean? So relatively B is not winding or unwinding, so both have the same velocity, so the rope remains same. So at this point rope remains the same. So what about this portion? So this is the first part and this is further second part. So this you have understood, right? At this second critical value, so the alpha is 0, so that means that there is no angular velocity for the drum, and so there is no relative velocity of B with respect to A. Both have the same velocity, and so the rope will neither unwind or wind, so they move at the same place. But before that, what happens? Before, say for example in this portion, so in this portion if you look at that, so particularly here in this portion we know that there is no slip. So what does that mean? If there is no slip, so what are the velocities of A and B? So you have seen, if there is no slip, so there is A here, there is a B here. So if this is a velocity here, and we know that interestingly that C is instantaneous center for no slip condition. So then what is this? The velocity of A and velocity of B seem to be on a triangle here like this. So what does this condition say? So that means that the velocity of point A is more than velocity of point B, right? Velocity of point A is more than velocity of B for pure rolling case. So what does that mean? So that means that this A here is moving faster than the velocity of B, or you can say that velocity of B is moving slower. So what does that mean? So with respect to B, A is moving forward, right? Okay, so that means that in this situation the drum is rolling over rope. Okay, so if somebody is trying to pull here, so if somebody is trying to pull this rope, then what happens is that the point A moves faster than point B, and then this rolls over and catches up with the person who is pulling it. Okay, so that is the situation. So whereas in this portion, so it is slipping as well as rolling, so it is not a pure rolling case, not even a pure slip case. So in which case this situation still holds good. That means that this is going to increase a little bit more because it's slipping, but it is still velocity of A is more than velocity of B. So here you can say that velocity of A is more than velocity of B in this portion, and in this portion velocity of A is less than velocity of B. And exactly at this point, so there is no rotation and the rope will neither wind or unwind, and it just keeps slipping with the same length of the rope. So I hope you have understood the two cases, where in the first case it is pure rolling up to here, and in this portion it's the rolling and slipping, and in this case it is more slipping than rolling, and rolling is taking place in the reverse direction. So in this portion, beyond this second critical value, then the rope will be pulled out more than the drum moving with certain velocity. So drum is moving with a little less velocity than point B, and so the cable is pulled out more. Okay, I hope you can find the difference, and I hope this graphical picture gives you idea. I wish that you look at these equations and try to find out what is this critical value. So this we have already solved. And what is this critical value? You can find out. In fact, you can draw another free body diagram where to calculate this one, there is no alpha. Alpha is 0 here. So you can use that condition, alpha being 0, and find out what f is and what the critical value is. So I hope you have appreciated the whole problem. The problem seems to be a little innocuous, but then there's several important issues here, and then I try to explain all these important issues. Okay, so we'll stop here for this moment and we'll continue in the next class. Bye.